Okay, now let's see what is mechanical energy, which may the name is familiar for you, and already we have introduced you uh, some forms of this energy. Actually, mechanical energy, by definition, is the form of energy that can be converted to mechanical work completely and directly by an ideal mechanical device such as an ideal turbine. So, first of all, from this sentence, you should distinguish between mechanical work and mechanical energy. Mechanical energy is, the reason to have to do a mechanical work. And as you may guess, two main forms of mechanical energy are kinetic and potential energies. These two are familiar forms of mechanical energy. And please notice that thermal energy, which is not mechanical energy. Why? Because it cannot convert it to work directly and completely. I mean, to mechanical work. So, however, you usually can use the thermal energy to produce work, but the form of the energy, the thermal energy, is not mechanical energy. So only kinetic and potential energies are the forms of mechanical energy. Moreover, we have the other type of mechanical energy when in many engineering systems we use some kind of fuels, some kind of fluid to run something which it has sometimes flow rate, velocity, and also elevation difference. And this system may generate mechanical work by using a turbine, or it may consume mechanical work in pump or fan during this process. So this flow rate of this fluid also can produce mechanical work. So it is one kind of mechanical energy. And you should notice that this system do not involve any conversion of nuclear, chemical, thermal, or uh, to mechanical energy. The only form which it is uh, converted to mechanical work actually is due to its flow rate and velocity or elevation difference. And the system like this also do not involve any heat transfer or thermal energy transfer. Or we can say it not involve in any significant amount. It may involve like what we have for friction, but it is not significant compared to the mechanical energy of or flow energy actually. This kind of system also are this kind of energy also are mechanical forms of energy because they are due to the uh, just flow rate, velocity, or elevation difference, which is kinetic energy, as you can see, guess from flow rate and velocity, or potential energy due to the elevation difference. So the energy which comes from the flowing of fluid is also kind of mechanical energy. Here we can see some example of that. We may have a combination of turbine and generator. Turbine is a device actually, which has some plate like what you can see here, and flowing of a fluid will cause to turning of or revolution of this shaft. This shaft is uh, also attached to a generator. Generator is a equipment which can convert mechanical energy. Here we have a revolution of the shaft to the electrical energy. So this turbine and generator will produce electrical energy by converting mechanical energy of the flow or fluid flow by this turbine. This energy which comes to the turbine, first of all, is related to the difference in elevation. You can see here, point 1 and point 2, we have a difference in elevation of the fluid. So because of this elevation, we have potential energy. This potential energy can be used to run this. It can be also converted to the kinetic energy to run this turbine, then produce electricity. So turbine can do this, and you can see here how is it for point 2 and 3. Also we have that the maximum uh, power which this system can produce, or W dot max, or energy rate actually, is equal to m dot delta E max. Delta E max means change in the maximum change in the total energy of the system times mass flow rate of the fluid, which is also equal to uh, the change in the potential, or the rate of change in the potential energy of the fluid, or simply because this Z1 and Z2 is like Z1, Z actually Z from Z4, Z1, we can write this equation. You can see here this distance is h. So maximum work rate is m dot gh, because P1 is equal to P4 equal to P atmosphere, and V1 is equal to V4. And to see more closer this turbine and effect of this flow and that turbine, we can write again this equation for point 2 and 3, which is actually entrance and the output of the turbine. Then we can again write this equation m dot delta E max to calculate the maximum work rate which we can get from this system. So the concept is this: here we have a fluid, we are going to produce electrical energy by that. How? Or useful energy by that. How we can do that? We can use this turbine. Fluid flow to the turbine, produce energy. How much is the maximum energy? Because of the energy which we have for this fluid is potential energy, because of the difference in elevation of the fluid. From here it is flowing to the downside, but up to here is the edge. Then also in the turbine we have another change in elevation, or simply we can write like this: W dot max equal to m dot delta E mechanical, change in the total mechanical energy of the system. We have m dot, or mass flow rate of the fluid, and total change in the mechanical energy of the system is due to the change in the pressure in the system, P2 minus P3 divided by rho, or simply we can write this equation. We can write this equation, this equation should be like before, but we can write this equation because V2 and V3 is almost equal, and Z2 and Z3, this part, are also uh, more or less equal. The change in the uh, mechanical energy in this system is due to the change in the pressure of the system. So mechanical energy is illustrated by an ideal hydraulic turbine coupled with an ideal generator. In the absence of irreversible losses, the maximum produced power is proportional to a change in power, the water surface elevation from the upstream to the downstream reservoir. In other words, this part, as much as H is the bigger, longer, it means more energy is there to convert it to the mechanical energy here. And secondly, it depends on the drop in the water pressure from just upstream to just downstream of turbine. The pressure also here will change. This change in the pressure is also another reason to produce mechanical energy by turbine. We have also reverse direction for this when we have a pump and we use pump to change mechanical energy from this uh, electrical energy to mechanical energy, which is only in reverse direction like what we have here. But the calculation is more or less same. So mechanical energy of a flowing fluid per unit mass is this much. The maximum equal to P divided by rho plus V power 2 divided by 2 plus Gz. This is due to elevation. This is due to the change in this is change in potential energy or the energy potential energy, kinetic energy, and also this is due to the pressure of the system, the energy. And mechanical energy rate actually can be calculated by this equation, m dot E mechanical or mass flow rate of the uh, fluid times mechanical energy of the system. Mechanical energy or total mechanical energy of the system we have calculated here. Just substitute here. Then this will give us the rate of mechanical energy of a flowing fluid. And mechanical energy change of a fluid during incompressible flow per unit mass can simply be calculated by this equation because we are going to see the change of the mechanical energy. We should uh, compare two different point of the system or two different state of the system actually. So simply pressure for the, this is a general equation, and in this equation we assume that pressure of the system will change from point 2 to point 1, from point 1 to point 2. The velocity will change and also the elevation will change. But as you know, G gravitational acceleration will be constant, and also the density because it is incompressible. And rate of mechanical energy change of a fluid during a incompressible flow, simply we multiply the change in the mechanical energy of the system by mass flow rate of the system. Mass flow rate of the system, m dot times this equation, which is the change in the mechanical energy of a fluid during a incompressible flow. As you can see here, our discussion is mainly about the mechanical energy of fluid because it is one of the most popular type of the uh, application of mechanical energy using, about the different dam and other, or about the wind turbine to to use renewable source of energy to produce mechanical, then to mechanical work, then produce electrical energy actually. Therefore, the mechanical energy of a fluid does not change during flow if its pressure, if P2 minus P1 is constant, so or density, velocity, and elevation remain constant. Mechanical energy of the fluid will be constant because we don't have P2 and P1, they are same. We don't have V2 and V1, they are just V, and also we don't have Z2 and Z1, it is Z, or this is simply 0, this is 0, this is 0. So the mechanical energy of the system, the change of mechanical energy of the system will be 0 if we don't have any change in elevation or velocity or pressure of the system. Okay, let's see in an example how we can use this information for to calculate the uh, energy which we can get from a wind turbine, or how much is wind energy. Wind energy, as you may guess, is one kind of mechanical energy because it is a fluid and it flows, and we can use its flow to produce or to convert to the finally to electrical energy and initially to mechanical energy or as shaft work. So what we have here is a site evaluated for a wind farm is observed to have a steady wind at a speed of 8.5 meters per second. Why it says steady? Because the flow, if it is not steady, it will be much hard to solve to find the velocity for the to put in our equation. So here the wind is steady, means its velocity is almost constant. Then we should determine the wind energy for A per unit mass, B for a mass of 10 kilogram, and C for a flow rate of 1,154 kilogram per second for air. So we should determine the wind energy for three different conditions. What we have here, as I mentioned, is a wind turbine. We know wind speed, how much is it, and also we have mass flow rate of the wind. So first, let's see what can be our assumption. Wind flows steadily at a specified speed. Where we find this assumption, how we can get this assumption, because of what is mentioned in the question. Then the only harvestable form of energy here is the kinetic energy, because no change in the flow of the air is like this. So no change, this is the flow. No change in it is not like this. No change in the elevation of flow. Only its velocity, the kinetic energy, the velocity of this uh, fluid, which is air, will produce kinetic energy. So wind energy per unit mass of air is equal to E, or kinetic energy is equal to V power 2 divided by 2. We have velocity 8.5 divided by 2. Unity conversion, because we are going to have the energy per unit of mass, the A part per unit mass. So per unit mass, energy of this wind is with the wind with this speed is 36.1. In B part, we should calculate for a mass of 10 kg or kilogram. So wind energy for an air mass of 10 kg. Simply, we just multiply the mass which is given times the energy for each kilogram of that mass. 10 kg, and energy for each kilogram is 36.1 joule per kilogram. Simply by multiplication, the energy of the wind for 10 kilogram of the uh, air here in this example will be 361 joule. Okay, this is for mass. How about when we have mass flow rate? Wind energy for a mass flow rate of 1154 kilogram per second. Then again, simply we can find uh, energy rate actually, energy flow rate for this. So if that is equal to, we have mass flow rate, simply we should multiply that to the energy of the system, and that times E. E is the mechanical or kinetic energy, which we already calculated for this air in this example, and the mass flow rate is given. So that is equal to that E 1154 kilogram per second times how much energy we have for air here for 1 kilogram 36.1 joule. Again, we should use this unity conversion to convert our unit to kilowatt. So the energy flow rate, or simply power, which we can get from this turbine, when the flow rate is this much, will be 41.7 kilowatt. As you can see here, we imagine all of the wind energy or mechanical energy or kinetic energy of the wind is converted to the uh, energy which can get by the turbine. However, in real world, we don't have something like this. So here was an example to show how we can use the uh, energy of the wind to produce useful energy or energy flow rate for our applications. Okay, next we will discuss about energy transfer by heat. Up to here, initially we started to talk about the energy transfer of a system. I said they have two different methods for energy transfer of a control system, or three different methods for also a control volume, which mass also can be transferred. But here, up to here, I have discussed about the energy transfer by work. Now I'm going to tell you how energy can transfer from system to surrounding or vice versa by heat or thermal energy. First of all, let's see what is heat. Heat is a form of energy that is transferred between two systems. If you recall previous slide, heat is energy which comes from the actually uh, mm, latent and sensible energy, which is related to molecule motion of the system. So the form of energy that is transferred between two systems or a system and its surrounding by virtue of a temperature difference. This is very important. If we don't have temperature difference, so energy cannot transfer as a thermal energy or heat form. As you can see here, here is an example to show how will be direction of the heat transfer or thermal energy transfer. Imagine we have three different cans in three different temperatures and in a room with temperature of 25 degrees Celsius. The first can temperature of first can is 25 degrees Celsius, same as the environment, no heat transfer. If temperature of the can is less than uh, temperature of the air or heat of the air or temperature of the air, actually not heat. Heat is the energy, temperature is the characteristic actually. energy heat is a kind of thermal energy, or is thermal energy actually. So if temperature of the can is less than temperature, which is our system, less than the surrounding, which is uh, air in the room, then thermal energy will transfer to the can. And as you can see here, as much as the temperature of the can is lower, these heat transfer from the surrounding to the system will be higher. This heat or thermal energy transfer rate, joule per second, which is also mentioned here. Temperature difference is the driving force for heat transfer. The larger the temperature difference, the higher is the rate of heat transfer. But you can also see 25 degrees Celsius, 15 degrees Celsius, difference is 10 degrees Celsius, and 25 degrees Celsius, 5 degrees Celsius, difference is 20 degrees Celsius. So its transfer rate here is higher than, or you can see double compared to for this can. And here you can see in schematic of how can be energy transfer for a closed system. It can be by work or heat. If there is temperature difference between the system and surrounding, it is energy transfer is thermal energy transfer or heat transfer. If work, but for this kind of energy transfer, we need to have temperature difference. If there is not temperature difference, we may have work or energy transfer or work transfer by system. So energy can cross the boundaries of a closed system in the form of heat or work when mass is constant for that system. Because of that, actually we call that closed system. And if we have insulation means and adiabatic system means we don't have any transfer between system and surrounding by using this insulation material, then the only method for energy transfer is work by system or on system. So during an adiabatic process, the system exchanges no heat with its surrounding. And you should notice we only recognize this energy transfer from the system to surrounding if the heat transfer happened through the boundary of the system. For example, in this baked potato, the skin of the baked potato can be our boundary of the system. So you can see here heat transfer or energy transfer between system and surroundings by heat, and it cross the border or boundary of the system, which is the skin of the potato. Then how we can calculate this energy transfer from the system to surrounding or vice versa. As I said, and you may recall from heat transfer subject, the heat transfer uh, its unit, because it is the heat is thermal energy, its unit is the joule. Then simply to calculate heat transfer per unit mass, we should divide heat transfer by mass of the system. So heat transfer per unit mass is Q divided capital Q divided by M, or its unit also is kilojoule per kilogram. And if amount of heat transfer, if the heat transfer rate is constant, now there were no change with time in the heat transfer between the system and surrounding, then the total heat transfer can be calculated by this. We just multiply the rate of heat transfer by delta T, which is the you know duration of that heat transfer. For example, we are going to know how much energy or thermal energy is transferred from that potato on the room during 10 minutes. We can use this equation. The time, the duration is important when you are going to know how much heat is transferred, the amount of the transfer, not its rate. The rate uh, should be calculated per time. And if the amount of heat transfer uh, rate actually is not constant with time, I mean initially, because usually the system is like this. However, we may use this equation in our calculation, but usually the heat transfer is like this. Why? Because with if let's go back to our example, if we put that potato, which its temperature is higher than the surrounding temperature of the potato, for example 50 degrees Celsius, surrounding 25 degrees Celsius, if we just leave it on the table in the room, its temperature will start to decrease. After a while, its temperature, for example, after 5 minutes, temperature will be 40 degrees Celsius. Then temperature difference between the potato and surrounding is different. Initially, it was at 25 degrees Celsius. Now it is 15 degrees Celsius. So as I said, higher temperature difference means higher rate of heat transfer. When this temperature difference is lower, rate of heat transfer also will decrease. So usually we should use this one. I mean, the rate of heat transfer for with time will change usually. But for simplicity, we may also use this equation in many of the examples. But heat is not always like what we know today. For many years, the nature of the heat was a big question for scientists. What is heat? One of the what you may know about one of the units for energy which we have these days, calorie. One of the theory was about the heat was this one, that it was thought the energy is an invisible fluid called the calorie that flowed from warmer bodies to cooler ones. In other words, um, heat was assumed as a substance, a fluid. However, nowadays we know it is energy. It is nothing, separated from the substances. It is characteristic of energy of substances which come from the motion of the molecules. So current theory is kinetic theory, which treats molecules as tiny balls that are in motion and thus possess kinetic energy. This kinetic energy is thermal energy actually. And the energy associated with this random motion of atoms and molecules is heat. And this is also, I think, just a repetition of what you know. Heat transfer mechanisms. We have three different methods for heat transfer from system to surrounding or vice versa. Conduction, convection, and radiation. The details of these three methods of heat transfer is out of our scope in this book. Is mainly related to heat transfer. However, we just deal with the amount of heat transfer, not the method, and so on. So conduction heat transfer is the transfer of energy from the more energetic particles of a substance to the adjacent, less energetic ones as a result of interaction between particles. In other words, two substances should be in contact, or the heat which is transferred in one substance from one point to the other point. molecule is attached to each other. What about convection? The transfer of energy between a solid surface and the adjacent fluid that is in motion. This is important. So we have a solid surface and a fluid which is in contact with that surface, and also it is in motion. If it is not in motion, we have it transferred by conduction between two stationary material. But if the fluid is in motion near the surface, we have convection. It transfers between the fluid, which is in motion, and the surface. And radiation, which is the transfer of energy due to the emission of electromagnetic waves or photons. Electromagnetic waves are some kind of waves which are not mechanical. They can change the energy of the substances when they reach light. You know, the simplest example is the sun array or visible. The visible is only one of the waves which reach earth or surrounding, and we have infrared and so on, is according their wavelength. But generally, you should know that radiation comes from these electromagnetic waves, which come from the material due to their temperature. Actually, they are they have this kind of radiation. This radiation reach the other material and will change their temperature. So by that slide, we finished the our discussion about the heat or thermal energy. Now let's see how energy is transferred by work. Work is like heat. It is an energy, but it is interaction between a system and its surrounding. And this energy can also, like heat, cross the boundary of the system. So generally, when the energy which cross the boundary of a closed system, it is important. Boundary, they are keywords. Energy crossing boundary of a closed system. If it is not heat, so it must be work. And as you know, heat is easy to recognize. If driving force is temperature, it means energy transfer between system and surrounding is heat or thermal energy. And if we don't have this kind of the temperature difference, or the energy transfer between the system and surrounding does not effective on the temperature of the system or surrounding, this energy transfer will be work. It seems to be easy, but later when we discuss about, for example, electrical energy, you will see why it is important. When electrical energy comes to the system, we should deal with that as work or heat or temperature. Later we will see. So more specifically, work is energy transfer associated with a force acting through a distance. Any place we have force, and that force is acting through a distance, we have work. Simply we call that Fx later will be F as a force, X as a distance. Later we will see what I mean about the work. So work is the energy transfer associated with a force acting through a distance, like a rising piston, a rotating shaft, an electric wire crossing the system boundary. Right? If you can see the difference between the uh, work and heat, which is not that much clear. But rising piston and rotating shaft, it is easy for you to understand are work, not temperature or heat transfer. All of them are associated with work interaction. And when we have work or heat, the sign of the this energy transfer is also important. Heat transfer to a system and work done by a system are positive, like what you can see here. However, later I will discuss about it here also. We can write Q in, Q out, W in, W out. And heat transfer from a system and work done on a system are negative. It is important for your calculation. When you do calculation to understand how much is the total, for example, energy transfer by system, if you write this sign incorrect, the total energy transfer may be different from what you calculate. Alternative to sign convention is to use the subscripts of in and out to indicate direction. This is the primary approach in this case. So usually we use Q in and Q out. W in, W out. You should bear in mind this method of using these subscripts. Heat going out from the system to surrounding, Q out, coming to system, Q in. So Q in positive, Q out negative, and W in, W out also. Heat transfer from a system is negative. Work on system, these two are negative. So this is also important. The total work we have for system is for whole system, whole mass of the system. Sometimes we are interested to know how much work is done by system per its unit mass. Again, we do this because we are interested sometimes to compare different systems with different mass. How we can compare them? By which one is more efficient? Which one use more efficiently use the energy to produce work, for example. So simply we can do this, divide the W or work of the system divided by M or mass of the system. So we have also another definition, which is power. Power is the work done per unit time or kilowatt, or simply we can say the rate of work or work rate of the system. Then how we can compare heat and work. These two are important because, as I said, these are two forms of possible energy transfer of system. Both of them are recognized at the boundary of the system as they cross the boundary. So no cross the boundaries by work or heat, we do not consider them. So both of them are boundary phenomena. It is not, they are not characteristic of a system like mass of the system. Heat and work only can be distinguished when they cross the boundary of system. Moreover, systems possess energy, but not heat or work. So what is in the system is energy, not heat, not work. Heat and work only on the boundary. This is very important. And both of them are associated with a process, not a state. We don't say how much is the work in point one, how much is the work in point two. We say how much is work is done by system or is done by surrounding on system during, for example, process A, process B. So during a process, we have this work. For example, when you bring something up or when you change position of something, the place of something from point one to point two, during this process, you are doing a work, not in that place. We don't have work, if you do not move something, for example, you have not done any work on or for that. Unlike properties, heat or work has no meaning at a state, which is, I think, obvious. We don't have work in point two. We don't have work at point one. We don't have heat in point one on point two. We have heat only during this process. Both are path function. In other words, their magnitudes depend on the path followed during a process as well as end space. We call these kind of functions, these kind of properties actually or parameters as path function. Properties which are uh, valid for the state, which state we call them point function, like velocity, like because for example we can say how much is the velocity at point one, how much is velocity at point two, how much is mass in point one, how much is mass in point two. We call them point function. So properties are point function have these properties which are point function have exact differential like this. We can simply write this equation integrated from point 1 to point 2, then you can simply write V2 minus V1 or delta V, changing the velocity of the system or even volume of the system. But for path function, they have inexact differential. So we should write like this. We use this delta, not D, when we write integral for these properties actually, then their values will be like this. For example, this is point 1, point 2, we are going to how much is work during, from point 1 to point 2. So we should write like this finally, W1 to 2. W during this process, process 1 and 2, work during this process, not delta W. We don't have any work difference for these 2 points. We have work during this process, but we have volume difference between point 1 and 2, or velocity, even velocity for them. But here the value. You can see volume here is 5 meter cubed, here 2 meter cubed. But what about work? Work should be 5 for this process.